mechanical or chemical pressure, then these materials, if they are not already topological, can undergo band inversion through these mechanisms to become topological, and they're protected by mirror symmetry and U and charge conservation, as Vidya pointed out, in contrast to regular TIs, which is hamburg and U1. And then of course, beautiful work done with Vidya to characterize the surface states in this material, and in particular, we will be focusing today on the 001 direction, because as I'm going to explain, that is where we see the strongest difference of these surface states with regular TIs, because there we actually see surface states that are tunable, and it's this tunability that we're going to exploit to look at the effects of strain on this surface. So then this is data by the hood and Vidya, just to note how there's these two, they come in pairs and they lie along two orthogonal mirror axes, distributed by four-fold rotation symmetry. So this is a nice picture from the Higgs group, in which it illustrates very nicely the differences between regular TIs and TCIs, just so that we can get a view for what we can expect in these materials. The Dirac points in regular TIs occur in odd numbers, and they are pinned at the high symmetry point. And so under time reversal, it goes back into itself, and hence under something like strain, there is going to be no effect. Whereas in these TCIs, they are not constrained to lie along the high symmetry point, and as we saw, that they can be tuned along this mirror axis. And this is our tunability, and since they always occur in pairs, which means that under a field such as strain, they can move oppositely, such that overall it does not bring time reversal symmetry, but they can move in opposite directions along this mirror axis in a continuous fashion. And again, this tunability is going to be what is going to give rise to the kinds of effects that we can see here. So Vidya already showed this data, and this is showing how through a different mechanism, changing the alloy composition of this material, that one can shift the position of these Dirac cones closer and closer towards the zone boundary, so that at the transition point, so there's a transition from a topological material to a trivial material, then they disappear. And this is the alloy composition, but we get a similar effect from strain. So then to see what strain does, we can we can look at the symmetry analysis to understand its effects. And if we do preserve all four-fold symmetry, then we naturally expect that strain pushes the Dirac cone in an equal manner towards or away from the zone center, and continues to preserve the four-fold rotation symmetry. And if we break down the four-fold rotation to two-fold rotation, then naturally we do expect the Dirac cones, to have a pair shifting towards the zone center and a pair shifting away from the zone center. And if in this case we break the mirror symmetry, such as with shear strain, then naturally we do expect the Dirac cones to move away from the mirror axes in such a fashion. And so this is the way in which we can parameterize the different kinds of strain that we can apply to this system, and hence alter this. And as Vidya pointed out, that the movement of these Dirac cones is similar to graphene. However, because of the crystal symmetry in these materials that is different from graphene, in graphene there is only one way in which strain can rotate these Dirac cones, whereas here we have three independent ways in which we can manipulate the Dirac cones in this material. This symmetry analysis was supported by ab initio calculations, in which here they did calculate how different types of strain will alter and change can cause firstly a phase transition into the topological phase, and then subsequently push away the Dirac cones away from the zone boundary. So we see here the three different materials that at a certain onset of strain, then we start to see the Dirac cones appearing. This characterizes how far away they are, and they do move away. So this is consistent with altimetry analysis. And because of the nice linearity of the Dirac fermions, we can make this identification of strain, of the effects of strain with a gauge field. Whereas in the case of non-relativistic fermions, there would also be additional terms of k dot a, and so the identification is not as smooth or straightforward in that case. So here is where we see that the lattice symmetries can give rise to different number of independent coupling constants for the strain, such that this allows us to write down for a particular valley. For a particular valley, we can write down the effects of vector potential, and it's given by the strain tensor and the coupling constant. So all of that was for strain generically, and now we can look at what happens in particular. What is the profile of the strain as we do get in these bilayer systems? We had seen from Vidya's very nice animation how the difference in the lattice constant between these two materials gives rise to causes a buildup of strain, and this strain is then can be relaxed through the formation of dislocations, so edge dislocations, where you should imagine a whole row of atoms that are now missing running through the system. And these rows of dislocations occur at periodic intervals, as can be seen from this TEM image, which is now seen from the top, in which there's a superlattice of dislocations. And so you can see that one of these blocks is probably on the order of 10 nanometers, so that's about